Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. So we were doing examples, and let's continue to do that. So I had figures 1, 2, and 3, 1A, B, C actually. So we discussed about turbulent jet, right, and its similarity with a laminar boundary layer and so on and so forth, right. Now, we have this plot here, okay. We have this plot here. Right. So this one, right? So the energy in a plane jet, and we have all these plots here. And as you can see, for example, we have a plot here with the circle markers, and this is labeled as production, right? Then we have another plot which is advection. It looks like that. Okay. Then you have this plot which is diffusion. Okay. And then you have another one which is called dissipation. Right. Now this is a numerical. This is not an experimental result. It is a numerical result. So now the question is, this is the example. So we're going to look at this. Okay. So our example. So for the plot shown in Figure 1C. Okay, A, what equation do we solve, right? What equation do we solve to arrive at the terms shown right? So arrive at the terms, or basically, you can say, or plots. Essentially, what we're looking at here is this is plots, right? Okay, 1C, right? And explain. And B, comment on the energy exchange. At the center line, okay, jet half width, and at a distance sufficiently away from the jet. Right? Now A, okay, what equation do we solve to arrive at the term shown in Figure 1C? Okay, now I think that is a straightforward question, because we've done this in detail. I'll still sort of just write it out. Okay, we use the mean mechanical energy equation, basically here subtracted from the instantaneous equation, and then we get a certain equation. Okay, so let me just write this here. So this is the mean mechanical energy equation. So mean mechanical, I'm not going to write these details. The mean mechanical energy equation, okay, subtract, right, or essentially we subtract this, right, plus the instantaneous mean mechanical energy right? And what we get is this. This is something that I'm going to write down, but this is something we've discussed in detail and written out earlier, but I'm still going to write this down, okay? So it looks something like this, okay? So let's use different colors. So say rho right? Now that is equal to this tilde xi, okay, or better still, let's just continue to do that, del xi okay, that, okay, and we take a mean of that, okay, minus rho and del xi of uj. This, right, plus tilde xi of uj nu del ui del xj plus del uj del xi, that mean, okay, minus nu del xi del uj del x I, and we take a mean of that. Okay, then the left hand side, right, let's just say this is O, okay, then the right hand side this is 1, okay, this is 2, this is 3, and this is 4. Okay. Okay. That. Okay, so this is something that we've done earlier, but I'm still sort of reminding ourselves, okay? Then, what do these terms mean? So we basically subtracted the mean mechanical energy equation from the instantaneous mean mechanical energy equation, and this is what we get. And then, this is what the terms mean, okay? This is the left-hand side, okay? This is rate of change, right, of mean turbulent K. Okay, then the first term is convective diffusion of turbulent energy. Okay. Second one is production of turbulent energy. The third term is work done by, this is work done by turbulent viscous stresses and the last term is turbulent viscous dissipation, right? So the question here is, what equation do we solve to arrive at the terms, or basically the plot shown in figure 1C. So let us just look at 1C. So this is the plot that we're looking at, right? We have 1, 2, 3, and 4. We have 4 of these plots out here, okay? And the question is, what equation do we solve, right, to arrive at these terms? So the equation that we solve, is essentially this. This is the equation, right? So the left-hand side, this one, is the rate of change of turbulent KE, right? So this is the rate of change of mean turbulent KE, right? The first term, this is the first term, right? This is convective diffusion of turbulent energy, right? The second one here, second term here, is the production of turbulent kinetic energy, right? The third one is work done by turbulent viscous forces. This is the work done by turbulent viscous forces. And the last one is turbulent dissipation, viscous dissipation. Okay. Now, let us, if we look at, so basically that, okay. So that's the first question. That's the first question. Now, let us now look at the plot in detail and see what we're looking at. So comment on the energy exchange at the center line, jet half width, and at a distance sufficiently far away from the jet. So let's go ahead and do that, okay? And we can maybe, jot down a few salient points, okay? So maybe we can jot down a few salient points for B, okay? All right, so if I look at this now, right? So let us see. Now here, you see, this one, the x-axis is essentially the y by delta, right? And the y-axis is all the energy, right? And this is the energy, the quantity of each is different. So production, advection, diffusion, dissipation, right? So we have 4 of these, and this basically gives us the rate of change of total, the mean kinetic and turbulent kinetic energy, right? Okay. Now, so this is the distance. Now, if you see y by delta is equal to 1, right? So y by delta is equal to 1. So delta here is actually the half width, and if that's so y by delta is here, okay? So y by delta is 1. So then this is what we are looking at. This is the plane, right? Y by delta is equal to 1. So then if y is 2 times delta, then it's slightly far away from the jet, right? And if y is 0, which is essentially this line, which is at the center line, so essentially what it is that this line, actually, this line is y is equal to 0, this is the center line. Okay, so let's just say this is the center line. So then this one, right, is at jet half width. Okay, this line is jet okay, so this is jet half width, okay, and this one is far away from jet. So these are the three lines we are looking for. Okay, let's just do that. So this is the center line that we're looking at. Okay, then this is the jet half width that we're looking at, and this is jet which is far away. Is that right? Okay. Okay. Now let us just say if we are y is equal to 0, which is here, right? This is the line. So y is equal to 0, what you see is that the advection is 0. Okay, before I do that, let's just look at so advection, diffusion, dissipation, and production. Okay. Now what you see here, if it is y is equal to 0, which is at the center line, right, the advection is actually, so if you see here, this is the point, right? Right? So here, this one, the advection is 0, right? Advection is 0, okay? Then the dissipation is negative, actually. If you see, this is the dissipation, right, which is actually negative. Then we have a slightly positive advection, right, advection, and a slightly positive diffusion, and a positive diffusion, right? So why don't we write that? Okay, let us go here and write that at the center line. That is our question, right? So the question is, at the center line, jet half width and a distance sufficiently far away. So at the center line, okay, so we have, so work done by turbulent viscous stresses and turbulent viscous dissipation, production, and convective diffusion. Let us just, okay, so here, what are the salient points? Okay, so what you see is advection is equal to 0. Advection is equal to 0, right? So if you see, this is the third term, right? This is the third term, and if you look at this, yeah. So advection is equal to 0. Let us write this down first, okay? Advection is 0, and then we have diffusion. Diffusion is negative, right? Sorry, the diffusion is actually positive, right? Diffusion and the production, oh, I'm sorry, actually the production is 0, right? Yeah, and advection and diffusion are positive. Okay, let's do that. Okay, so the production is 0 and advection and diffusion are positive. Advection and diffusion, okay, now these are both positive, right? These are both positive and non-zero, right? These are non-zero. Okay, then C is dissipation, right? And this is negative non-zero, right? And production is actually 0. So if I go here, if you see, this is the dissipation. This is the dissipation, right? It is negative, right? It is non-zero negative, and this is actually the production, which is actually 0, right? So I think basically this is at the center line. This is at the center line, okay? Advection, diffusion, dissipation, and production, okay? We might as well even make a chart out of this, okay? So why don't we do that? So if let's just say that we have, let's make a chart out of this, okay? So we've got so we had advection, diffusion, dissipation, production. So this is advection, dissipation, diffusion, and production, okay? So, and then we have the center line, we have jet half width, and far away from jet, okay? So if I were to do that, what we just wrote down is that advection and diffusion are positive. Advection and diffusion are positive. Diffusion are positive, non-zero. Dissipation is negative and non-zero. Production is 0, right? Dissipation is negative and non-zero. Okay, now let us go and look at the jet half width. So if I look at the jet half width, okay, which is here, right, what I see is that this is the advection, right? It is nearly 0. The advection is nearly 0, okay? So the advection is nearly 0, okay? The advection is nearly 0, right? Production is the highest. Production is considerably large, quite positive, you know, compared to the previous case. So the production of energy is, pretty high, okay? Nearly maximum, okay, the production. So the production is nearly maximum. So it reaches the maximum production just before the jet half width, okay? So this is max, okay? And you can actually put in the values also if you look at this, okay? That's the production. Then this is the advection. This is the diffusion, and the diffusion is negative, right? Diffusion is negative, and yeah, diffusion and dissipation are both negative, right? These are both negative. Negative, non-zero. Okay, and then far away from the jet, if you go far away from the jet, well, you can see that nearly all of them is equal to 0, right? So this is the diffusion. Okay, sorry. So this is the diffusion. This is the production. this is the advection, and this is dissipation. So they're all nearly zero. Okay, that makes sense, right? So these are nearly zero. Right. So what we can see here is that as the, when we move from the center line, when we move from the center line to the jet half width, right? So the production goes from zero to maximum. Okay, and again, even the farther you move away, the production becomes zero. So this is production of kinetic energy, turbulent kinetic energy. So these the turbulent kinetic energy. So I think I didn't write that, but because this q square, right? What is this q square? Let me write that here, okay, to sort of drive home the point. So this q square actually, right? So this one, this is the K, right? So we are looking at the maximum value of that, and that happens a little before the jet half width, and then it starts decreasing, right? So a little just before the jet half width is reached, the maximum production is happening. So if you go here, you can see that, right? So this is a jet half width. The maximum production is happening somewhere just below, before the jet half width, and then it starts decreasing, from there. So at the jet half width, it's nearly the maximum, and then it continues to decrease, obviously, because this is a turbulent kinetic energy, right? So the farther you move away from the jet, the U dash, V dash, W dash values start decreasing, and therefore the production value also decreases, and finally it's nearly zero. So the farther away from the jet, you go, the production is decreasing, because the turbulent quantities basically go to zero as we move away from the jet. So that's something that we've spoken about. Okay. Now dissipation and diffusion. So therefore, when we move far away from the jet, of course, all the terms. If you're going to look at the numerical terms here, right? So these are all the turbulent quantities. So as you move far away from the jet, obviously these things are going to become negligible, and therefore all these terms go to zero, and hence that's what is showing up. Okay, that's what is showing up. So jet half width kinetic energy is the turbulent kinetic energy is not yet. So you can see it is at the jet half width, the advection is zero, right? The advection is zero. The dissipation is negative, right? And the diffusion is also negative. But the production of kinetic energy is like the maximum, nearly the maximum at the jet half width. So most of it is essentially the kinetic energy, turbulent kinetic energy is being produced, right? And dissipation and diffusion is really are almost a negative. Okay, right. So that's what we essentially gather from this plot here. Okay, and I also find it interesting that at some points, let us look at this, discuss this a little bit. For example, okay, so for example, look at this point here. Okay, this one. Okay, so if I were to look at, say, this point, okay, then again, this point, there are some more points here, some more are here, like this, including this one. Right, so I am looking at this location. Right, so if you look at this point, for example, let's just say this one is, say, point A, B, C, D, and E. Right, now if you see at A, right, so this is the slightly away. It is between the center line and the jet half width, somewhere there. So if you see, this is the diffusion, and this is the diffusion, and this is the production. So they're actually same. See, they're crossing paths, so to speak, right? So at this location, so I might as well write this, okay? At location A, so this is the production, right? And that seems to be exactly equal to the diffusion. Why don't we write that? Okay, so at the location, say A. So the production, this is the production, right? So that is same as diffusion. So production and diffusion, they are same, right? So here essentially production is equal to diffusion. So that's at location A. Okay, what's at location B? This is also nearly, it's near the center line. So here it's nearly kind of starting out. The jet is kind of starting out, beginning to spread. So here, if you see, this is the diffusion and this is the advection. The diffusion is equal to the advection. This is at point B. So at point B, right? So diffusion is same as the advection. Okay? So at point B, you have, this is the advection and this is the diffusion, right? So advection is same as the diffusion. So here, okay, then we look at C, right? So C is the point where, if you see, this is production. So production is same as advection, right? It's interesting. It's interesting. So let us see. Let us see. So so at C, right? So at C we have the advection the same as production. At C, the advection is same as production. Okay, so advection is equal to D, right? So D here, or let's actually, well, because B comes first, so I could have written this as A actually. So anyway, so D here, this is the production, right? And that is equal to diffusion at D. So at D, okay, production is equal to diffusion. So D is production and diffusion. Yes. Interesting. Right? Again, production is equal to, so you could say D and A are kind of similar points. Let us see. So if you see A, this is A and this is another D. Yeah, and you see they are same and the values are almost nearly same, right? The values of diffusion, production are same at both these locations. Production is equal to diffusion and they're same at A and D. That's interesting, right? And then E, here advection is same as diffusion. At the point E, right? So at point E, advection is same as diffusion. So advection is same as diffusion. This E also is getting repeated the same as B, right? So this is advection is diffusion. So if I look here, you see, look at this point E, right? So advection here, so here, if you see here, advection is the same as diffusion. This value is negative, right? So here also, at B actually, this is diffusion and this is advection. At B also, this term, okay, at B also, advection is equal to diffusion, but this is positive, and at E it is negative, right? So B also advection is equal to diffusion, but this is actually positive, right? And here, actually, this is negative. But they are same, right? However, these values are same. The production is equal to diffusion. So this one, so this here, this A and D, the values are actually same, right? Is equal to, okay? So these two are actually same, okay? They are same values. And here, B and E also have advection is equal to diffusion, but then this is positive and this is negative, right? So it is interesting to sort of, notice these things in here, and I'll kind of, leave you to sort of think a little more about that. And ideally, the way to think about this is also that, for example, is it possible to sort of, enhance, say, the production even more, taking out something else? And what would that mean, right? Taking out another term for that matter, right? And in the numerical analysis, if you see here, right, all the terms are kind of non-zero and significant. It's not like they're not significant. They are significant. So the only thing is that at the jet half width, right, you get the maximum production and you get the minimum dissipation, right? And the advection, this is the advection. Advection is zero, right? Advection is zero at the jet half width. Advection is zero at the jet half width, right? Production is nearly maximum, okay? So the production is nearly maximum. The advection is zero at the jet half width, right? The diffusion is less than, the diffusion is sort of less than the negative minima, okay? And the dissipation is slightly more than the minima, right? So dissipation actually starts increasing. So the interesting thing is that just before that, where you have the maxima, the production maxima, which is here, right? The production maxima is somewhere over here, right? That's where you also have the dissipation minima, right? And after that, the production starts decreasing and the dissipation starts increasing, right? It changes slope, actually. Okay, and it's interesting also that the production curve, if you see, it is it's kind of what to say. The production curve is symmetric, right? In the sense about its maxima. Okay, unlike the advection or the diffusion, because if you see the diffusion, the negative minima is much more, okay? The negative minima is much more than the positive maxima, okay? So similarly, if you look at the advection also, so the positive maxima is, much more than the negative minima. Okay. Okay, so that's essentially the this plot that we looked at. Okay. All right, so what we essentially spoke about here is that how do we get this equation? I mean, how do we get these plots for one? Okay, so what we said is that, this is the equation that we solve. Okay, this is the equation that we solve. So essentially what we're saying is that the rate of change of mean turbulent kinetic energy, right, is a sum of the convective diffusion, the production, the work done by turbulent viscous stresses and turbulent viscous dissipation, right? The rate of change of mean turbulent kinetic energy. And what we then saw is that at the center line, right, there is actually no production, right? So the sum, if you say the rate of change of total kinetic energy, that actually depends on the advection, diffusion, and dissipation. So there's actually no production at the center line, right? Now, at a jet half width, on the other hand, the production is maximum, nearly maximum, right? And advection is actually 0, right? And there is non-zero dissipation and diffusion. Far away from the jet, of course, these are, these are zeros. Okay, and we also looked at these 5 points where it is interesting to see that. At the point, for example, A, and at the point D, right? So at the point A and D. So if you see here, this is the point A, this is the point D. Here, production is equal to diffusion. Yeah, production is equal to diffusion, and these. It is interesting is that the values are same of production and diffusion at both these locations, and this is also symmetrically placed about the jet half width, right? So A is before that and D is after the jet half width, but this is symmetrically placed. It's nearly equidistant, right, from the jet half width. Okay, and on the other hand, however, we have at the point B as well as E. If you see here, if you look at this point, if you look at B and if you look at E, right, advection is equal to diffusion. So here advection is equal to, so both places advection is equal to diffusion, but then the values are different. Okay, at the point B, the values are positive. At the point E, the values are negative, but the magnitude is also different. Okay, the magnitude is slightly positive, and here it is. Well, actually, it seems like the magnitude might, the magnitude is actually much higher. Okay, so magnitude is also different. Okay, so I think, so we will we will have to stop here because I don't want to start something, the new one, because what we'll start looking at, so that's that essentially. Okay, so this is the energy exchange. Okay, I think the point I'm trying to drive home here is that there is an energy exchange in a turbulent flow in such a way that there's more than one way that this energy is being the energy exists, let's put it that way. Okay, there's more than one way that the energy exists, right? And at any given location, which is away from the jet, right? So this is the central line, and now we are going away. This is the central line, and we are going away from the central line. We cross the jet half width, and then we go away from it. Now, at any given location here, as we move away from the center line, the energy is contained in the turbulent, flow in more than one. The energy exchange actually is happening in more ways than one. Right, so it could be production, it could be advection, it could be diffusion or dissipation, right? And we looked at salient points as to how things are happening. And however, as we move sort of farther away, as we start moving farther away from the jet, all of these things sort of become negligible. They become zero, of course. right? Okay, so I think we will stop here. What we'll do in the next class is to look at the, so let's just say, so what we will look at is this, okay? Now we will actually look at this plot. Okay, so I will erase all that. Okay, so this is essentially the lateral velocity or the v velocity, and this is something that we haven't looked at, and we'll look at this. Okay, so the next class, okay, that's what we are going to look at, the lateral velocity, and right, so we'll do that. Okay, so this is something we spoke about, the mean mechanical energy equation, and how the energy content of the turbulent jet there is an energy exchange, right? But we can sort of figure out in what way that energy change is happening. So as I have written here, advection, dissipation, diffusion, production. Now all of these ways are not present at all times, you know, and that is interesting. And we looked at salient points of that plot. Okay, so I'll stop here, and we'll talk about the lateral velocity in the next class. Okay, thank you.